All right, we're going to do these free response questions now. This first one is about Archimedes, was given a crown purported to have been made of pure gold, which had a known density at the time. His task was to determine whether the crown was in fact made of pure gold or if less dense and less valuable silver had been mixed in. Suppose you're given this task in addition to equipment commonly available in a high school laboratory. List the measurements that would be made to determine whether the crown is made of pure gold and give each measurement an algebraic symbol. State the equipment that we use to make the measurement, then outline. Okay, so basically it would probably go something like this: is I would, put the crown on a spring scale to measure its weight, force W, then immerse the crown still on the spring scale in water to get its what's called apparent weight, which I call FA. I explain how the measurements made probably would be used to determine whether the crown is made of pure gold. I didn't really include any steps to reduce experimental error. I guess I would maybe say something like, do 10 trials and average the FWs and FAs to reduce error. I have no better answer than that, frankly. Okay, so what are you going to do? I'm going to say the buoyancy is FB, which is the weight minus the apparent weight. I'm going to say solve for the crown's volume in force buoyancy equals density of the water, volume of the crown, gravity. Okay. And then let's see. The mass of the crown is weight over gravity, right? So then the density of the crown is mass over the volume of the crown compare to gold and silver's density, right? Okay. Oh, new situation. Now consider two spheres of equal volume, one made of more dense gold and the other made of less dense silver. Both spheres are dropped into the same vat of water and allowed to reach the bottom, coming to rest. Draw the forces acting on one of the two spheres when it is at rest at the bottom of the vat. Okay, well then at rest at the bottom, it would have a force buoyancy, a force normal, and these two together would equal the force weight. Okay. Which sphere, gold or silver, experiences a greater buoyancy force? They both have the same. The force of buoyancy is density, volume, gravity, and it says equal volume. So both have the same force buoyancy since they have the same volume. But gold has more density. So it's going to have more mass. It's going to have more force weight and the same force buoyancy, right? It's asking which experiences a greater force due to the floor of the vat, right? So if gold has the same buoyancy force but greater force weight, the gold needs more force normal from the bottom of the vat. Okay, consider a tank of water. Its density is 1,000. Base area of 0.5 meters squared. The height of the water in the tank is 0.8 meters. Calculate the gauge pressure at the bottom of the tank and the total force due to only water at the bottom of the tank with the units. Okay, so gauge pressure is density, gravity, height without atmosphere. So 1,000 gravity and the height is 0.8. So that's going to be 8,000 newtons per meter squared, which is pascals. And then force equals pressure times area. That'd be 8,000 times the base area, 0.5, so that'd be 4,000 newtons. Okay, a sphere of mass 10 kilograms hangs from a spring scale. When the sphere is submerged into the water, the reading on the spring scale is 20 newtons. Calculate the volume and density of the sphere. Okay, well, the buoyancy force is 100 newtons minus 20 newtons, so that's 80 newtons. Remember, this weighs mg is 100. This times 10 for gravity is 100. And then the reading on the spring scale is 20. So here's what it would look like. Here's the mg, which is 100. Here's the reading on the scale, which is 20. So here's the force buoyancy, which is 80 newtons, right? Okay, so there you go. Newtons, newtons, newtons. Okay, so 80 newtons is density of the water, volume of the entire sphere of underwater gravity. So 80 equals 1,000 times volume times 10. So volume is going to be 0.008 meters cubed. And then we know the mass is 10. So the density of the sphere will be 10 kilograms over 0.008. And I'm not doing the math in my head. 10 kilograms over 0.008 is 1250 kilograms per meters cubed. All right, so here we go there. The sphere is removed from the water. A small hole on the side of the tank near the bottom is unplugged, causing water to emerge, travel distance d horizontally before landing on the ground. The sphere is again immersed in the water, and it's observed that the distance d increases. Afterwards, observe the distance d gradually decreases, and then explain why that is. Okay, so let me draw what I'm to understand here. Okay, so here's the water coming out, but then what happens is that the sphere's in the water, so the water is going to come out even farther, right? So why is that? Well, there's two things you can say. You can say that since force buoyancy is the water pushing up on the sphere pushes down on the water, increasing the pressure. That's one thing you could say. Or you could say that immersing the sphere raises the water level. Yeah. When the sphere goes in the water is now at a higher level. Is the water level, which makes the hole deeper in the water, right? And so there's more pressure, right? Because pressure is rho g depth. Okay, either way, you have to talk about pressure, and then you got to say if pressure increases, the speed of water emerging from the hole increases. And then you need to say something, maybe P equals 1/2 rho V squared, or rho GH equals 1/2 rho V squared. So either you say that the water line went up, or you say that the pressure goes up like right here. Either way, that makes the water go faster, and faster water will go farther as a projectile, right? Okay. Top diagram shows a device with no mass of its own and consists of a cap of area A connected to two springs, force constant K. The free end of each spring is connected to a rough surface. The device is fitted into the bottom of a tank of water density rho, plugging the bottom of the tank and preventing water from flowing into a vertical pipe. Bottom diagram. The static friction mu with the sides of the vertical pipe and the springs are both compressed. The distance x equals in order to fit the device into place. If the water level in the tank is higher than the height h, the static friction is broken and the device falls and the water flows. Okay, how the value of h, the height change, if k were increased? Okay, So here's what I'm going to say. I'm going to say more K, more spring force. That results in more force normal, because what's happening? The springs are pushing against the walls of this pipe. So the force normal is pushing back on them, and that makes there be more force friction, which means there can withstand more pressure, which means you can have more height before it breaks. Okay, how would the value of H change if A were increased? Well, then you would have more force from the same height of water, right? Because pressure equals F times A. So you have more area. Oh, F over A, sorry. So if you have more area, you have more force, right? F equals PA, I really meant to say. So if area goes up, force goes up, and that means that it's gonna fall out of place. So we have to compensate with a lower height. Okay, derive expressions for the following in terms of all those letters. The maximum static frictional force that could act on the device. Okay, so force friction is equal to mu force normal, and the force normal in this case is equal to K times X. So that means that the force friction, maximum force friction, is mu times K times X, and there's two of them. Oh, yeah. So there's two of them. So the maximum static friction net is actually 2 mu kx, one for each contact. Excuse me. The value of maximum water height that would not result in the device slipping out of place. Okay, so here we go. Force is equal to pressure times area. The force is 2 mu kx. X is the compression of springs. Pressure is density, gravity, height, and the area is A. So then if I divide, I get 2 mu kx over density, gravity, area. That's the height. That's part B2. Okay, here's my answer to B2. Does my answer to B2 support my answer to A1? More K is more height. So A1 more K more height is what I said. So on C1, I'm going to say yes, since K is in the numerator, more K more height. And then for A2, I said more area, less height. Well, for C2, I'm going to say since area is in the denominator, more area is less height. All right, so that's the deal there. Well, that's the 3 free response questions. I hope you enjoyed watching this set of videos.